session about efficiency, how to make a power supply to be efficient, how to choose the right inductor, and how to calculate the inductor according to the efficiency. First of all, when you think about selecting a storage inductor, it's very important that you know you are working on step down, or step up, or buck boost converter. Now, I will explain first for the buck converter, for a step down converter. I have here an example for a 15-volt input, a 5-volt output, 1 amp continuous current, and the switching frequency is 200 kilohertz. Now, when you calculate the inductor according to the duty cycle, you will have a duty cycle of roughly 33%, and the rated current on the output will be exactly the same current which will be supplied from the storage inductor. So the current will be 1 amp through the inductor, so you have to take in consideration about the saturation and about the rated current himself, about the self-heating. Now, you can switch and calculate with the ripple current. You can play between, I will recommend a minimum ripple current of 20% and a maximum ripple current of 40%. And according to these two different values, like 20 and 40%, you may have, because it's very simple, 1 amp output, 200 milliamp or 400 milliamp ripple current. Now, in calculation with a simplified formula with a duty cycle, switching frequency, ripple current, output current, we will have some different value. Like for 20% ripple current, we will have a bigger inductor, which is 83 microhenry, and with a 40 or 50% ripple current, we will have an inductance roughly by 33 microhenry. So this is the two limits, which I will say, okay, we know what is the maximum, what is the minimum roughly, but we will choose for a good performance. I always recommend take the middle value, which would be in this case something like a 56 microhenry for start beginning. Then you measure the efficiency, and then you can take the 83 microhenry, folder in, look which is the efficiency now, then take the 33 microhenry and look what is the efficiency now. And now you can see what is the most dominancy. Dominancy of the RDC, because the RDC in the same size, in the same package, will be at 83 microhenry, the biggest, and the smallest will be at 33, or it's a core losses dominancy, and then you may have maybe 83 will be the highest losses, or maybe the lowest losses because of the core, or maybe even 56 microhenry will be excellent to begin. Again, the output current, you have to take care, but the output current, if you have an output current like 1 amp, and you have additional this ripple of 500 milliamp by 50% maximum ripple current, the maximum inductance current will be 1.5 amp. So I will select the inductor which has at least at 1.5 amp no saturation at all. You have to take care because the saturation definition is not a standard definition, and every manufacturer make his own saturation definition. At Virtual Electronic, I will say 90% of the inductance, you will see a saturation definition of 10% drop. As soon the inductance drop 10% from his initial value, we will say it is saturated. Sometimes, because of the core size, because of the construction, or maybe because we follow some competitor manufacturer, we have also sometimes 30%, 35% saturation, which in this case I will not be able to use it. It's not so good. Okay, now in this case 56 microhenry, 30% ripple current will be okay, something maximum 30% ripple current, even higher. It will be like a very simple inductor in the shielded package, because I would recommend to use a shielded inductance. If you followed my first webinar about the EMI, you will see the big difference. You can even try the biggest one, the 68, 56, 68, and try out which have the less ripple and less losses in this case. When you talk about boost converter, now we turn back. We have 5-volt input, 15-volt output, again 1 amp, again 200 kilohertz switching frequency. We will change the formula. Now we have 66% duty cycle, almost 67. The rated current to the inductor will be now 3 amp, because you have to consider that you put the 1 amp, which is the output current, and you put also the additional current from the source together, and you put all both together in this inductance. So that's the reason why your current into the inductance will be much, much higher. So now if you talk about 20 or 40% ripple current, we will have 600 milliamp or 1.2 amp. Again, if you use this formula, you will have the smallest inductance by 50% maximum ripple of something like 10 microhenry, and by 10% the minimum ripple current, which you will choose in this case 56 microhenry. Never go less than 10% ripple, because then you will not have enough magnetizing force in the inductor to make a magnetizing induction, and then you will have not a very safe function. And also never go above 50% ripple current, because in this case you may have a trouble that you will have a lot of EMI problem to fight and lot of losses again in core losses for the inductor. So maximum 50% and minimum 10% ripple. A value between 20-40 is much better. Again, the optimized value would be, I will start with 33 microhenry again, and then change 27 or even 22 to see what happened now if I decrease the inductance. Do I have more dominance of the DC losses, or I even increase to 47 and look what happened now with my core losses? It will be something not so bad. Again, the output current now with this 1 amp plus 50% ripple maximum plus the inductance current maximum, we will have a 3.75 amp. I would say a saturation minimum 3.5 amp. Even higher, I would recommend to use again the inductance in a linear version where the inductance have no saturation at all. Inductance versus current curve, you can see always in the data sheet what happened with the inductance if you apply a DC bias load. And I would choose in this case at least 3.6 amp inductor, again shielded one, because that is welcome and it is much, much better. You can try the value between 22 and 47 to see what is for your recommendation much better. What will happen with the ripple current if you increase the inductance or decrease the inductance? If you look with your scope to this inductance current, you will see that with 56 microhenry in comparison with the 32 microhenry, the ripple current will decrease. So this is something which is exactly make that the core losses will be dominant or not so dominant. Generally, we can talk about if you have a buck converter, the output maximum output current from your DC-DC converter, it is the current which is passing the inductant himself. If you have a boost converter, it is highly recommended to use an inductant which has at least this formula modified, this simplified formula, which should have this inductance, no saturation, and also to not running hot, because also thermal heating is very important for efficiency. The best thing is if you have a good efficiency, like more like 90%, you will see that your inductor will not running hot, and you will have, if you have already 90% efficiency, very rare will happen that you will have also EMI problem. How to inductor, how to be choose that not be saturated. Again, the Emax in this case, I would say at this value, the inductance should have no saturation at all. If you have the space, of course, it's sometimes a space problem. You have to make some compromise, but I would recommend if you use this kind of very simplified formulas, you can have no problem and no trouble to choose the right inductance. For design tools, I can recommend to use software which is free of charge, which is not so different to use, like this RedExpert. If you go to this website, va-online.com/RedExpert, this is something which you don't need to download it. It's a very simple. Now I have to see if I can. Can somebody give me a feedback if you can see my browser in the chat room? Please just say yes, I can see your browser. No, it's a gray box. Okay. Now I have to go back to my share. Okay. I will check here now. Share my screen. One. Okay. Can you see now my screen? Okay, now it's running. This is the red expert, like I told you. If you choose the power inductor, very simple. You just click on this power inductor, and then you have now possibility between buck, boost, APIC, or just to calculate losses. Now, if you go to the buck converter, press this simple button, and now you can put your minimum input voltage, something like we have 5 volt, then 5 volt. Oh, it was 15. This is buck. Okay, this is 15 volt, 15 volt, 15 volt output, 1 amp, switching frequency 200 kilohertz. Now the delta ripple current, I would say 30% ripple. The diode voltage drop 0.3, and you can see already the software tell you which kind of inductor would fit to your design or not. Now, if you click on this first inductance, you can just pull and drag here, and you want to compare it with something else. And another, this is a TPC series. If you want to compare with a PD series, again, drag and drop, and now you can see the different saturation curve. Even you can make bigger. Now, you know that your output current is 1 amp. Now, already by this point, at 1 amp output is first the red line. This is the TPC, a tiny power choke, very simple. Already he has a saturation drop to 44.1. The other one, the PD power inductor, it's 46.6. So now it depends if you have a H problem, if you have a big size problem, then the TPC is quite very nice, small inductor. The other one is a little bit bigger. Even if you don't have space problem, then you can go even to higher version. You can even limit the size. If you have here something like a height problem, you can say I have a height minimum, so no maximum, a height maximum of 10 millimeter, and then tuck, sort out everything which is not fit to your design. If you have another problem in the length or something like that, you can choose. But the nice thing is, as soon you click on this device, display details, it tells you that you will have here a total losses of 237 milliwatt, which means 207 milliwatt DC losses and 330.4 milliwatt AC losses, core losses. Now, if you compare with the first one, it has 166 milliwatt total losses, a warming of 24.1 Kelvin. The other one, it's already 33 Kelvin. If the warming is for you a massive problem, you can even try something like this, 13 Kelvin. Now you can choose the third one. You have multiple options here. Even if you want to just open the PDF, you just click on the PDF, you can see the step files or even the 3D model and also the inductance saturation. All these values what you will find in the data sheet are included in this red expert. And the red expert doesn't use a simplified Steinmetz formula. I will come back to that. He's using really measured value. We did measure all these different steps and all these value which you will see in this graph. If you go to this graph and you will see this inductance, you will see that many inductance steps are measured values. So it's not just a simplified Steinmetz formula, which is not so valid in the duty cycle when you're not running on the duty cycle of 50%. In this case, we are running on a duty cycle, let me check, which I choose 35%. We have a 35%. So the duty cycle error based on the Steinmetz formula will be not so good in this case. Free of charge, you don't need to register. If you register, you have multiple functions. You can even change different language here. We don't have every language, but the most language spoken are already here located. And if you register here, you will have a own login, and you will have also some revenue. Of course, you can share this by email, or even you can post on Twitter. I don't know why my colleagues from marketing have also Facebook and Twitter, but I guess it's more for fun. But even you can generate here a link, a unique link for colleagues, or if you ask for samples or something, you just click on this button and you already have all this, but you choose here different inductance value. Okay, now turn back to the red expert. I hope you can see now my Red Expert, just a short feedback. If somebody can say, yes, I can see your presentation, it will be very helpful for me. Can you see? Yes, thank you. Okay. So another tool, another issue which you have in the total losses, when you calculate the total losses, you have partial DC losses because generated of the copper losses, and you have the AC losses caused by the skin effect, proximity effect, the AC losses because of the core losses, eddy current, hysteresis losses. All that is calculated in this Red Expert. Normally, people are using this simplified Steinmetz model, and the Steinmetz model is generated with a sine wave generator, and the measurement is quite very complex. What we did take our inductor and we did measure for the efficiency, for the losses on front of the inductor and after the inductance. And we did use a simple class D amplifier. Based on our loss model, it's a real-time measurement. So we are pulsating a voltage to an inductor, and this is not a sine wave. So in this case, we have some values for different frequency, and then sweep from 10 kilohertz to 10 megahertz. We have collecting all this data from different core size and from different core material as well. And after we implement all this data, we have generate a nice complex formula, which is valid and can be reproduced on the measurement. In Steinmetz model, because you generate a sinus model, you use in the BH this area a very big loop with a sinus wave. This is valid only for core losses. You're not considering the wire losses, proximity losses, and also you don't have a sinus wave in your DC-DC converter. In our formula, we use a rectangle signal, and we don't use the whole loop in the BH curve. And according to our model, we have much higher accuracy. If you compare now the accuracy for the Steinmetz formula and our model, you will see that our accuracy is not bad. Right now, one of my colleagues makes his PhD on this formula and also on this different measurements. We have a very accuracy in this case, and really it's reproducible. You can really measure it and excellent working. I would never was expected that high resolution, which is possible to achieve, and even override the DC range. So if you have a duty cycle, which is not 50%, if you have a duty cycle of 10%, or even if you have pulse skipping mode or burst mode, is working excellent and still reproducible. Additional, because we did use different material, iron powder, some different alloys, it's possible also to reproduce on not sintered cores, which in the Steinmetz formula it's valid normally only just in sintered called toroidals, mostly nickel zinc or manganesic zinc. We consider also the real shape, the mechanical size, the air gap which is inside, and also the winding structure. So it's quite more complex like the Steinmetz model, but it still works perfectly. Another simulation tool which I can recommend is the WebBench. If you go again to our website on the toolbox, if you press the toolbox button, you have possibility to simulate according to the TI chips with this WebBench optimizer, and then you can play with this button to optimize the efficiency or to optimize the cost or even to optimize the footprint. We don't have this super duper button, which is the lowest cost, the highest efficiency, and the smallest footprint. That would be very nice if you have this button, but it's always a balance, like in the natural everything. You cannot get everything by one single piece. You have to consider if you have high efficiency, maybe the inductor costs a little bit more, the chip is maybe a little bit more expensive. If you use the same chip and you want to have low cost, then you have to think maybe your EMI will be more expensive. Whatever it is possible to tune with this WebBench optimizer. Another nice tool what we did develop together with Texas Instruments, this wireless power charging, the G standard. Texas are manufacturing this chip, we manufacture the inductor, the receiver, and the transmitter coil. It can be also get from Farnell or from our website as well, or from TI. It's the kit including the transmitter, completely the development board, and also the receiver. I'm not so sure if you will get this G logo right now, because I think we have a new development where instead of G is called WE on the LEDs. I guess I have to check upload my picture. Different coils, even very, very small ones, and receiver coil, small like a fingernail, very, very small one. Even transmitter coils in a triple size if you want to make multiple position. Very nice efficiency in the G standard. Right now you can achieve with the first generation chip up to 5 watt, and Texas is already on the market with some new chips. The development kit is just working on. It will be also released hopefully end of this year. It's possible to achieve even 15 watt in G standard, the second edition. Some other information: if you don't want to build yourself your DC-DC converter completely by discrete components, there are some other modules which are completely including everything in the small IC. These are completely IC DC-DC converter, where the capacity, inductor, controller, MOSFET completely included, and you can replace one-to-one or completely DC-DC converter. So actually this power module concept is a lead frame, and on the lead frame we have built in this TO package the inductor. This is a X-ray from our Magic module. You can see the IC, the die. There are the input-output capacitors and everything in the lead frame, a nice package in different voltage QFN package as well, and C packages as well, a through hole in different voltage range up to 6 amp and up to 50 volt. So 50 volt doesn't have 6 amp, but up to 2.5 amp with 50 volt input, or if you don't have voltage higher like 6 volt, you can go up to 6 amps as well. In the C package, it just released this month the 1 amp. We have also the 1 amp right now. The inductor himself, somebody did ask right now, just check the chat room. It's a shielded one? Yes, it is shielded one, always a shielded one. More information you can get from a trilogy of magnetics. If you get this book, or the power module ABC, or ABC of capacitor, it's a very nice book which you can get more information about the RF products and also about the magnetics, what happened into the inductor, how to calculate the inductor, right? More details. It's also about the modules himself. If you still have any questions, just please place on this chat. I will try myself to give you an answer in this chat room, and also the PDF will be available to download. Most important, when you design a DC-DC converter and did not work from first switch on, you should not give up. This is very important. It's always a solution. It's always something hidden, which is maybe you don't see by first. But if you call us, we try with worldwide local salespeople to try to help you and find the right inductor for your application. Doesn't matter which country you're located, we have always, in every country, I would say in every industrial country, we have our own salespeople, and in country where we are not acting by our direct sales, we have even Farnell. Farnell is also our distributor, and you can get in touch with Farnell and get everything from stock from Farnell as well. So this is my location. If you are in Germany, World Electronic is on the highway A6 between Heilbronn and Nuremberg. You can see our building from the highway when you pass by, and I am located actually around this corner. If you see on the right side on this corner down on the first floor, I am located right now here. Now don't forget please to participate to our quiz. It's very important. If you press that link, you will be directed of the TI side, and when you register on the TI side, there are some questions. And
has left the conference.
if you participate in the quiz, you can win something nice. Now I will check what is on the chat room.
Okay, right. So thanks for a great presentation, Laurent. While you begin typing your questions to our host, I'll take this opportunity again to remind everyone, like Laurent's just mentioned, that there will be a 2-question quiz available as part of today's 3-book set giveaway. I've posted the TI.com link to this in the chat window already, and you can see the terms and conditions for this giveaway along with the recordings and registrations on our main element14.com/webinars page. A link to the webinar series page is included in the chat window as well. And as well as also, I've just posted it on the comments of our this event's webpage on Element 14. As we get ready for the Q&A, I also want to note that all questions that are asked in today's session are being documented, and we will get the answers to those questions to you via a posting on the Element 14 page in which you registered. So if your question can't be answered during the time we have left, we'll do our best to post as many or all of the answers in the comments on that page. Likewise, any questions you think of later, at a later date, simply post them on the web page and we'll get to them in due course and relay with Laurent to get them answered. So we will notify all quiz winners at the week commencing March 9th, and we have just under 30 minutes or 25 minutes left for questions, so quite a good period of time. So Laurent, I will return the presentation to you now for Q&A.
Thank you, Jane. So somebody asked here, can you advise the topology for high gain DC-DC booster about 20 times amplification, current about 10-15 milliamp, a very, very low current, very high amplification. So in this case, definitely I will use a transformer and not just a simple DC-DC by inductor. I will definitely use in that case a transformer design. If you have that kind of high amplification, small, I would say if you have so small current, a small flyback would be also fits with the inductance will be quite difficult. It would work, yes, with a high millihenry inductance maybe sometimes. It depends also on the switching frequency, of course. But I will try in that way definitely a transformer flyback topology. So I think somebody asked again for Magic. Yeah, the Magic, they have shielded inductor. I think I answered already that. Okay, flyback with high boost gain, also a trouble. Yes, it's not so simple. That's true. You have to filter them very well definitely on input. You will need to focus, of course, for the 3rd, 5th, and 7th harmonics definitely to have a good filtering. That's definitely a trouble. I agree with that. I know. If anybody did ever made a background LED or LCD background lighting, know what I'm talking about. This is not so easy, but yeah, you have to do a filtering. That's correct. What's another question here? So if anybody has right now a design which you have to work out right now, we can play directly with this red expert if you like to introduce and already see what means the losses totally. And if you have a nice thermal camera, I did it myself first also to try out if these guys really calculate correct. I make the demo board and put to the infrared camera and then measure the temperature, the real temperature in the inductor with all the dissipation from the PCB to consider as well. And I was really impressed that it was just 2 Kelvin difference between the red expert calculator and what I did measure on the infrared camera. And that I put also in the video. It will be available soon on our website because I was so impressed. I said, okay, I have to share this impression because this is something really, really nice, which I did fight for almost more like 70 years ago, like a design engineer. When I did make some DC-DC power supplies, I had that problem that efficiency would already that time very high request. Today, if you build something, you need at least 85–90% efficiency is a minimum, I would say, if you build now a DC-DC converter. So nobody trusts to ask something. You can send me by privately a chat, no problem. I will not mention from who is coming, no problem. So please feel free and ask any question regarding inductance or EMI or efficiency.
We'll give it 1 more minute, and otherwise we can give everyone some time back, Laurent. So give it 1 more minute. So feel free to type in the chat window any more questions you may have. That would be great. Otherwise, at a later date, as I mentioned earlier, please feel free to also post them on element 14, and we'll come back to you as soon as possible. Okay, we'll give it 1 more minute.
Name not recorded. Has left the conference.
Yes, somebody asked which browser is the best one. I'm using Firefox. I have the last version. It's okay. It works also with Chrome. Chrome is a little bit faster, like always, but it's optimized for all browsers. Even at Safari, if you have a tablet, iPad, it works perfectly. It's not so nice to introduce the data, but it works quite not bad. So I just can give you an idea. When I'm working with the browser from Firefox, I press, after I logged in this window, I press the button F11, function 11. If you press function 11, it's maximize the browser to your screen, and you don't have all this side information, and you have more space to see more data. That's what I like. If you have a HD resolution at least, or even 2K resolution, you can put this on F11, maximize your screen to the maximum full screen, and you have a better. Somebody asked, how does the switching frequency affect the efficiency? Well, as soon you increase the switching frequency, your inductor value will be automatically decreasing. At a certain point, you have to take care that if you increase too high the frequency, like if you go to 10 megahertz, you already have some switching MOSFET losses already quite not so good. And additionally, 10 megahertz already, the inductor will be very, very small. You will never need a 10 megahertz 100 microhenry. It's already enough 100 nanohenry. It's very small inductor indeed, but you will have to fight it again for the EMI. And then the EMI filter in consideration will also affect the efficiency as well. So I would say a good switching frequency today, it is something between 500 kilohertz to maximum 1–2 megahertz. Very, very rare. If you have really high current, you will use 3 or 5 megahertz. You can get from Texas chips without any problem, which they are switching at 8 to 10 megahertz. But it's always a balance. It's always a balance. And if you turn the button too high to the frequency and the inductor will be small, you will see that in other places you will need some other inductors, other capacity, other components to affect the performance. Okay, another question. Now it's nice. RTI vertical fully integrated chips for ultra low power. For IoT, yes, there are some special for energy harvesting. We talk about energy harvesting chips. There are some chips on the market already from TI, and we have also some special inductor for that. We talk about already energy harvesting solutions for very, very low power. So you can have output of 50 milliamp maximum current and already starting by 10 millivolts already, the DC-DC converter. Some other question, how does a saturated inductor affect the performance and anything else? Okay, first of all, if you saturate the inductance, the effect will be that you will not see this nice triangle current flowing to the inductance. You will see a partial triangle and then a high peak, and this high peak will have the problem that it will generate a lot of EMI problem, first of all. Second, if you saturate too high the inductor will start to have a major core losses. So you will put a lot of energy which you will transfer in magnetizing, demagnetizing, and in that case you will have overheating of the core, and the performance of the inductor will collapse. Question was how the saturation affect, how the inductor saturation affect the performance. Somebody asked, do the RedExpert CB converter calculator provide correct DC loss results when the feed-forward architecture is used? Yes, because it's again also when we use for the SAPI converter a calculation, it is not just a simple calculation, it's based on measured values. So also the SAPI calculator, especially when you use a coupled inductors, we have you can choose at SAPI converter two different inductor or a coupled inductors. I will suggest use a inductor, this coupled inductor on the same core, because there are really measured value. Another question, could you list some sign of incorrect inductor issues? Basically, how I would distinguish between inductor issue and maybe circuit layout capacitor, another problem. Wow, this is quite very wide question. Incorrect on inductor. First of all, incorrect inductor, it is for, I would say incorrect, it is to use a non-shielded inductor for a DC-DC storage inductor. For a DC-DC converter, for a storage inductor, I always recommend to use a shielded one. It has at least two benefits. One benefit is, of course, EMI, because it's shielded, it will not working like an antenna. And second, because of the shielding, you may have in the same size a very lower DC resistance, because we don't have to put the same amount of the windings in the same core to reach the same inductance value. And you will have a less DC losses, and you will have a better EMI. Disadvantage, I have to say it as well, you have a disadvantage, his saturation, it is not so good like a open magnetic field rod core inductor, because the unshielded version is like a vertical rod core to the PCB, and because he can have a infinite air gap, his saturation is much better. That's the advantage. But the disadvantage you will see in the EMI measurement chamber, and you will see the disadvantage in the RDC. For filter inductance, you can use non-shielded inductance. There's no problem, but not for storage. Another question, in a buck topology, what would mean signing an inductor? And the inductor makes more noise. No, an inductor, well, if you make a buck topology, you will need to use an inductor. Of course, an inductor doesn't make himself the noise. The noise is not coming because the inductor is in the circuit. The inductor, you charge energy in a non-continuous form with a switching frequency. You charge and discharge, you charge and discharge. Actually, you are generating the noise with the IC, with the topology, not when the noise doesn't come. Or maybe you mean the audio noise. This is something different. Somebody asked about a semi-shielded inductor for a DC-DC. Yes, we have some semi-shielded inductors in our portfolio. Personally, I will say this is a compromise. This is a compromise between size and EMI performance. Because this semi-shielding, actually it is an unshielded inductor where we put above these windings, we put epoxy glue with ferrite powder mixed. It's not the same like you have a shielding ring. if you make a measurement, I did done myself measurement with a near field probe, and you compare in the same DC-DC converter, the same inductance value, the unshielded, the semi-shielded, and the shielded version, it's a big step between semi-shielded to the shielded version. But also in the size is a big step. So if you don't have enough space to fit a shielded version and the unshielded version, it have to be used, at least I would say try to fit the semi-shielded one, because it's anyway better like the not shielded at all. I would say you will improve 20% of the magnetic field to keep inside, but not 80% like by the shielded version. In terms of EMI, a toroid is the best shielded inductance because his magnetic field cannot leak, cannot go out. But who want to use a toroid special today? Think about your mobile phone. Okay, the person say again, I was talking about the audio noise. Yes, the audio noise, it happened. Normally, nobody switch his DC-DC converter with 10 kilohertz, where human can hear maximum 60 kilohertz. When you're switching frequencies, something like 250 kilohertz, 500 kilohertz, you will not be able to hear that. A very, very high-fi freak, they say they can hear 22 kilohertz, which I have a good friend, he's doctor for years, and he say 16 kilohertz, a good violinist can feel it but not hear it. But what you will hear is some harmonics which happen in the resonant point. And what I had in my experience, I just take the inductance and turn on the PCB 180 degrees on the soldering point. Normally, if you look on the inductors, on the surface mount inductance, they have always a dot on the top. This dot means the beginning of the winding. And if you put this dot to the direction of the switch node, to the IC, normally they don't start to singing. In my experience was every time when the pick and place machine was not fixed to put the inductor in the right direction, some of the DC-DC converter in the maximum load start or even in the half load or not so high load start to make a audio noise, a very high frequency audio noise, and then with this solder the inductance turned 180 degrees, soldered back, and it was gone. One experience I had which did not help, it's turning around the inductance, and I find out, okay, the colleague did use a duty cycle which was not so good, and as soon we changed the duty cycle, it was already much better, and the sound was gone. So actually, if you are using that kind of pulse mode, sometimes it could happen, yes. Okay, another question. How would you measure the current in the inductor on the PCB? Do I need a shunt resistor? Well, when I measure the current in the inductor on the PCB, I take a wire, desolder the inductor and solder in series with the inductor a piece of wire which is big enough that I can put my current probe for my oscilloscope. I have a very, very tiny current probe, and I put it on the leg on the inductor. In terms of EMI, is not so good, but I can really measure the inductor current on the inductor himself using this copper wire. Just take a quite 1.5 millimeter, 2 millimeter copper wire and put the inductor soldered by hand. That's the simplest way. If you measure above a shunt resistor, if you have a space, then you can put that. It's also possible you have a precision resistance. Yes, it could be measured as well. So, okay. Could you please cycle to the slides once, please, very quickly. I will suggest you will get the PDF, and then you can go to the slide by slide. Very simple. Somebody asked, a DC-DC converter could as good as LDO with a correct design, or you will still use the LDO for low noise system? Well, of course, a DC-DC converter and the LDO is a big difference. If you talk about efficiency, then the LDO will never be competitive with a DC-DC converter. If you have a RF design and you have a very strict, less ripple current or ripple less current to the RF design, LDO is the best solution, of course. It depends. It depends on the application, honestly. I did use also a DC-DC converter when I did make my own mixer at my home. I had no problem because I did know what I'm doing with my DC-DC converter. And of course, I put some more effort, not just a simple LC filter, but with a simple PT decade, you can filter always the rest ripple until you have less than 5 millivolts ripple. And if 5 millivolts is fine, I don't know if I would choose a LDO just for 40% or less efficiency. Somebody asked if TI or Word make fully integrated chips for ultra-low power. Right now, we don't have that in our focus, definitely not. I don't know, TI, maybe you have to put this question directly to TI, field application engineers. I cannot imagine that they will focus right now on that. Ultra-low power in energy harvesting is interesting, but not completely integrated. I don't think so right now. Somebody asked if I would use a ferrite bead as output filter for a buck converter. If yes, would you make place more of the output capacitor before and after the ferrite like a P configuration? Well, actually, a buck converter have to be filtered on input. They are very aggressive in input. A boost converter, it's more aggressive, more noisy at the output. So definitely, if I would use a ferrite bead, which is working for losses higher like 10 megahertz, I don't think so that you will need to put on the output of the buck converter. I will use it maybe on the input. If you have a nice input filter on the buck converter, I will use it definitely on the input. On the output, if you want to filter the buck converter on the output, it depends which fragments you want to filter. You have to look with a spectrum analyzer, and if you have really some high frequency still noise, which is maybe not coming from your DC-DC converter, it's coming from the input already, and you just pass through, then yes, you can make a simple LC filter using a chip bead ferrite and a ceramic capacitor, low ASR, low ASL as well. Capacitor before or after the ferrite? After the ferrite, LC. Another question. Why are buck converter aggressive in the input and boost on the output? Somebody asked, why is buck converter aggressive on input and why on boost on output? Well, when you are making a buck converter, you have a source, which could be a battery, and now you take this current not continuously. Every time when the current is coming, you disconnect and connect. You take this current, charge the inductor,
has left the conference.
And that means that you will generate a wave on the input automatically because you're not taking the current continuously. This is by the buck. By the boost converter, you take the input battery, the source, you charge the inductance, and then after you charge the inductance, you put in serial again with the source, the battery, and the inductor current. You put these two, I would say, second battery inductor charged in serial, and then you put to the output. And then you automatically on the output, you may have a higher ripple like in the input, because the input is flowing always. You charge the inductance, or you put this current, not only just the inductance, you put additional current to put to the output. So the current flow is much more smoother, and you don't have this reflection. And that's the reason why a boost is more on the output, have a higher ripple and higher problem, because you even increase the current and you increase the inductance value, additional the charging the inductance with a high current, and then you want to transfer this current into the voltage, and you have automatically on the boost a higher EMI noise. Somebody asked how you use two inductors. I don't know exactly what you mean. I never tried to use two inductors in a buck or boost topology. I use two inductors in a SAPIC conversion. Or if you have a buck boost solution as well, sometimes possible. Somebody asked a certificate for the webinar. I guess is not, I don't know, you have to ask that from Farnell. Farnell is the host. I did not know if I have one. So I think we are on the end of the time, and I will give over now to Jane. Jane, are you here?
Lovely. Yes, I'm here. Thank you, Laurent. That's great. Thanks again to Laurent Folkel and to everyone for attending today. The slides will be made available as soon as they're uploaded. We promise by tomorrow, but we'll get them up there as soon as we get them PDF'd and our developers add on. So we'll get them there forthwith, and then definitely be there by tomorrow, if not in the next hour. And we've also had questions about the certificate. So as long as you comply with all the terms and conditions and you've attended all the seminars, yes, you will. The certificates are actually being issued directly by TI. And they've got a database that they've been keeping of all the attendees. Any issues or what have you, feel free to either post a comment on this event's webpage or email or put an app mention within feedback and support on element14.com, and the feedback and support team will follow up. But hopefully everything should work out swimmingly. So have a great rest of the day, everyone, and weekend, and goodbye for now, and look forward to welcoming you to the next set of webinars. Thank you. Goodbye.
Thank you too. I will say also goodbye.
Has left the conference.
Bis und later.
Name not recorded. Has left the conference.
Bonsoir or bon voyage or arrivederci. Okay. Bye bye.
Thank you, Laurent.